Okay, fossils part 2. You don't need to copy anything on this page, just anything that's in yellow. Scientists use various methods to determine the age of rocks and the Earth. So this whole thing is going to be on how fossils are dated. How do we know how old they are? Okay, first thing, number 1, that should be yellow. It's called the law of superposition. Fossils, remember, are almost always found in sedimentary rock. Very rarely are they found in igneous or metamorphic. The law of superposition states that in a series of sedimentary rock layers, the younger rocks normally lie on top of the older rocks. And if you take a look at this picture, where's my mouse? Down here, you can see, imagine these are rocks over time. Okay, the stuff on the bottom is going to be the oldest, and as you go up, the youngest is going to be at the surface. So if you find a fossil at the top of a layer of rock, it's going to be younger than a fossil found at the bottom. Okay, this is kind of showing you law of superposition. If you look, this is the Grand Canyon, that's the Colorado River, carving it out. The rocks up here at the surface are much younger than the rocks down here at the bottom. Once again, young at the top, old down here. Okay, number 2 is an index fossil. We've already talked about this. So as long as you know it, you pretty much don't need to copy it, but make sure you know it. An index fossil is like the trilobite, or this is an ammonite here. They're really pretty. It is a fossil that lived for only a short period of time. And if you find, let's say, that ammonite or the trilobite in a layer of rock, then you know that that layer of rock was formed in the time span of that index fossil. Oh, I'm sorry, we seem to be frozen. Oh, lovely. Okay, we're skipping this for now. Well, I'll play any videos for you in class and help you out in class. Okay, number 3 is the principle of uniformitarianism. And what that basically means is the present is the key to the past. The processes that shape the Earth today, the weathering, the erosion, the earthquakes, the mountain building, anything plate tectonic-wise, okay, that are happening today, are the same processes that have been going on for billions of years. Weathering and erosion didn't just happen. Volcanoes didn't just show up. All of this has been around for years. And that's what principle of uniformitarianism states. Okay, number 4 is an unconformity. I think number 4 and maybe 5, definitely number 4 is the one you really need to focus on. An unconformity is just a gap in the rock layer. It's a missing layer of rock. So it says missing layers of sedimentary rock that eroded away or were never deposited. Okay, so if you kind of look here, do you see how you have the wavy line in this top picture? That wavy line is showing an unconformity. That means something happened. Rock either eroded away or for some reason, no new rock wasn't deposited. Maybe that could be in the instance of it was covered with water. Okay. A disconformity forms between layers of sedimentary rock. So it would be sedimentary, sedimentary, a disconformity, and another sedimentary. Here's formation of a disconformity. You have deposition of the material. The oldest is on the bottom. You have it uplifted, meaning something forced that land up or the rock up, and the top parts of it were eroded away. Okay. Then you have deposition, so more sediment comes on top. And let me move this. Tilting and faulting of the deposited material happened right here, and I have to go over this with you in class. A non-conformity, it's the same thing. It's still a missing layer in the record, in the rock record, but this happens between sedimentary and non-sedimentary rock. So you might have sedimentary as the gray, the green could be igneous, the brown could be sedimentary, igneous, sedimentary. So if you have a missing layer in between sedimentary and an igneous or metamorphic, that's just called a non-conformity. Okay, and we'll go over this in class. Okay, this is real life, what a disconformity or a non-conformity would look like. See how you have some sort of syncline. Remember, synclines sink, they go down in folded mountains. You have some sort of syncline, but look, right here, you should have more of the rock coming up, but you don't. Instead, it was eroded away, and then this is brand new material deposited on top of it. So that's what a dis or a non-conformity would look like. Here also, and I'll go over it at another time, but you can see that this is also, if you actually look, This was a syncline or an anticline that's now on its side. And you can see there's some kind of missing gap here. There's solid rock in the background, there's solid rock in the foreground, but there's a missing gap here. And that's another way of looking at an unconformity. Once again, an unconformity is right up here. You have these layers of sandstone, and then all of a sudden the sandstone is missing here and a new type of rock has filled in. So that is a disconformity or a nonconformity. Once again, same thing. You have sandstone once again, and notice it has been pushed on its side or tilted, and the sandstone seems to be going sort of up and down. You can actually see an anticline right here. Okay, and then something happened here where all of a sudden you have the deposit going horizontal. So that is, in this case, this would definitely be a disconformity. Same thing here. Same thing here. Okay, here we go. The principle of cross-cutting relationships. A fault is a crack in the rock where one side can move. Remember, faults are associated with plate tectonics. Rock layers are always older than the fault. Okay, if there's a crack in the rock had to be there before it got cracked. So the rock layer is older. Okay, if you have intrusion of magma, remember that's when magma oozes up over existing rocks. Okay, the intrusion of magma has to have formed after the rock layers were present. Therefore, the intrusion is younger. The rock was there first, and then the magma kind of blurbed on top of it. An extrusion is when magma is forced to the top of the rock layers. Once again, the layers were there first, and then the magma literally cut through the layers and oozed on top, so the extrusion is younger. The principle of cross-cutting relationships states the cross-cutting rocks, such as igneous intrusions, are younger than the rocks they cut through. Okay, we're going to do this in class. If you like puzzles, this is going to be a really good little part of class for you. Same thing. This, I want you all to figure out if you think it is cross-cutting relationships, if it's index fossil, if it's an unconformity. What do you think is going on here? This is a perfect example of a cross-cutting relationship. Whatever this orange rock is here, which honestly kind of looks like shale to me, it looks like it's definitely sedimentary. That was here first. Then the magma oozed over on top of it. It literally cut through it. The rock is older than the magma. So the intrusion, this would be an intrusion, is younger than the existing rock. Okay, same thing here. You have this existing rock, and you have what they call a basalt dike. A dike is just when the magma oozes up through it in a thin crack. Okay, and so the intrusion is younger than the existing rock. Okay, relative dating, and some of this you might remember from 6th grade. Now, for relative dating, this is just trying to figure out which is older and which is younger. It's not an exact date. All you're doing is comparing the layers to each other. Okay. You have to think about the rate of deposition. The average amount of deposition is about 30 millimeters a year. So if you see a sample of rock and you find a fossil in there, and you want to find out when that fossil was laid down on top of the rock, you can go from the top down and subtract 30 millimeters a year to figure out how long that rock has been there, or the fossil has been there. Okay, principle of superposition, remember that states that older rock beds are covered by younger rock beds, so the youngest is at the top. And like I said, it's just comparing. That's all relative dating is. You're just looking at it and saying, oh, this one appears to be younger or older than that one. Absolute dating is when you start to bring in the chemistry. It's radioactive dating. It's the breakdown of a radioactive element such as carbon-14 into a decayed element occurs at a constant rate. So it's used to determine the exact age of something. Carbon-14 is used for anything that was alive, because anything living, whether it's a tree or a bug or a human or a water buffalo or whatever it is, has carbon in it. So if you figure out how much that carbon has broken down over the over its kind of half-life years, then you can figure out how old that sediment or that fossil was. Okay, half-life is the amount of time it takes a radioactive element to half decay into a non-radioactive element. Okay, looking at this, here's your relative dating on the left. You can say these shells are at the top, so they are younger than these trilobites at the bottom. For numerical dating, you can actually get a carbon-14 or a carbon sample from the trilobite fossil or from the shell fossil, and you can literally figure out how old each of those are. That's the numerical dating. We're doing that in class. Okay, did I skip something? That seems really weird. Nope. Okay, the oldest rocks on the moon date back to 4.6 billion years old, a half billion years older than the rocks on Earth. Evidence suggests that the Earth and moon formed at about the same time. In class, I want you to tell me, why is there a difference in that time? Okay, there's some other dating techniques that can be done, and notice they are not in yellow. Just kind of keep them in the back of your mind. I'm not going to test you on them. There's the tree ring, so I have one to actually show you in class. If you count the number and the thickness of the rings, you can figure out how old that tree was or how long it was growing or alive for. If you have a dark ring, that means it was a wet year. If there are lighter colored rings, that means it's a dry year. You can have seasonal climate changes. You can have the deposition of dark and light colored material called varve. And there's key bed layers of rock that become a time marker. Like I said, you're not tested on those at all. Where's my mouse? There it is. These are key bed layers. So if you see right here, how this layer right here is dark, and that dark layer goes over here to this mountain, you know that those layers were probably laid down at the same time. If you think of a volcano erupting and the ash that's falling, wherever the ash fell and accumulated, you know that that entire area is going to date back to the same time. And that's it. Bring your stuff to class. I will see you tomorrow.